So let us look at A. We want to show that the mixed Poisson process does not have independent increments. So whenever we want to show that two stochastic variables are not independent, there is a trick that we can use. So in general, we know that if two stochastic variables x and y are independent, then their covariance will be 0, right? So by contraposition, we can see that if the covariance of two variables is not 0, then that implies that these two variables are not independent. So we can prove lack of independence by showing that increments in the mixed Poisson process do not have covariance 0. Let us just recall what is the definition of covariance of two stochastic variables. So the definition of covariance of two stochastic variables is that you have to take the mean value of their product and then subtract the product of their mean values. And we will be calculating the covariance using this formula here, applied to the increments in a mixed Poisson process that are, so increments that are evaluated on two disjoint time intervals, s to t and x to y. So just to get started, let s be greater than or equal to 0, and let it be strictly smaller than t, and consider a disjoint interval x to y, like this. Then we can just start calculating. We can start calculating, let's say, well, what we want to consider are the increments, right? So the increments n of s to t and the increment from time x to y. Then we can start by trying to calculate the mean value of the increment from time s to t. What is that given us? Well, the thing is that this is a mixed Poisson process, right? So not only is it random in terms of the n being random, it is also random in terms of its parameter, its mixing parameter, theta being random. So in order to work with it, we kind of have to try to fix theta and do something with whatever is inside when theta is fixed first. So the thing we're going to do is, first of all, just realize that the mixed Poisson process can be written using its definition as such. And then I condition on theta and then take an expectation outside. So this holds by the double expectation property. And then what I can do now is realize this one thing, namely that given theta, the increment of n tilde from time theta s to theta t is just Poisson distributed with parameter theta t minus s. So what I mean is that, and this actually holds in particular because that the standard homogeneous Poisson process and theta are independent. So this is a necessary assumption. So basically what I'm saying is, given theta, when God has thrown the dice, when we found out what theta is, then we also know more or less how the mixed Poisson process will behave. So which kind of Poisson process it will behave as. And given theta taking on a specific value, then the mixed Poisson process will be will have increments that are Poisson distributed as such. So given theta, the increment from time theta s to time theta t is just the same as the increment from time theta s to theta t inside a standard homogeneous Poisson process. So what I can do now is I can continue writing, because now the mean value in such a distribution is just a parameter. So what I'm taking is essentially just theta multiplied by t minus s. And this is equal to the mean of theta, and I can take t minus s outside, because t minus s is just a constant. And I can apply exactly the same trick to calculate the mean value of the increment from x to y, and that will give me the result mean of theta multiplied by y minus x. So these two results together yield for me what the second term in the covariance calculation should be, namely that the mean of one increment multiplied by the mean of the other increment is given as the mean of theta taken from here, and then multiplied by the mean of theta again. So I take this squared, then I multiply by the interval lengths, the time interval lengths. Okay, so this is one part of the calculation for the covariance. I've done the means separately now, and the next part, I've calculated this thing, now I want to calculate this thing, right? So I want to find the expected value of the product of increments. Let's just see. The mean of n s to t multiplied by the increment from time x to y. Well, as before, I need to fix theta in some way by conditioning on it. So I say conditioning on theta, then I realize that this is just the increment in a mixed Poisson process. So by definition, it's written as n tilde from time theta s to theta t, and then multiply by n tilde from time theta x to theta y. So here I have the increments inside a standard homogeneous Poisson process from time theta s to theta t and theta x to theta y. And given theta, this thing here will just be Poisson distributed in one way, and this thing here will be Poisson distributed in another way, if I'm able to separate them from each other in some way. So let's just write up here, take the double expectation outside, and the first thing that I notice is, given theta, well, then this is just an increment in a standard homogeneous Poisson process, and it is thus independent from the other increment in a standard homogeneous Poisson process. So this holds given that I condition on theta. And thus, I am able to split the mean of their product into the product of their means. So I have the mean of n tilde theta s theta t given theta multiplied by the mean of n tilde from theta x to theta y given theta. Okay, and as established before, given theta, this increment is just the increment that I have inside a standard homogeneous Poisson process from time theta s to theta t. So its expected value will be theta multiplied by t minus s. And in the same way, the expected value of this thing given theta is just theta multiplied by y minus x. And thus this is equal to the mean value of theta squared multiplied by t minus s multiplied by y minus x. So now let's just sum up and see what we have. The mean value of the product of the increments is given by this thing here. The mean value of each of the increments multiplied together after I take the mean is given by this thing here. So I can conclude that the covariance of the increments should be equal to the mean of theta squared. I take this, right? And I multiply by t minus s multiplied by y minus x. And also, I subtract this thing up here. And I can take the t minus s and y minus x outside my parentheses. So this is all in all my covariance between the increments. And we can see that this cannot be 0 because each of the time intervals here have lengths greater than 0. And also what I have here is the variance of theta, which was assumed to be greater than 0. So the covariance between two increments is always greater than 0, which is the reason why the Mixed Poisson process does not have independent increments.